All right, so hopefully, there's not too many people still working on that final Excel assignment. So I've gotten a lot of emails. So let me outline this to get started. I mentioned a long time ago to start that Excel assignment because that first question is going to be stuff we did a long time ago. So I'm getting emails like, how do I even approach this? It goes all the way back to that file. We're looking at that Indiana weather, and you're simply using that norm.dist function. Right, so this goes way back before confidence intervals. For that first question, the Indiana weather data file is going to be really a template. For questions 2 and 3, we're going to be looking at that YouTube kind of likes, dislikes file that we use. We have an example of proportion there, an example where we had a known population standard deviation, and an example where we only had a sample variance. So, excuse me, I will be available today and well, yes, today is the due date, so I'll be available today 3 to 5. All right, so I'll be in my office from 3 to 5 if you want to stop by, kind of last minute questions on the Excel assignment. Other than that, we've got those practice problems. Once again, try to reiterate, these are just practice problems, right? They're not worth any points. I know there's a point that kind of show up next to them. I can't turn that off in Canvas for whatever reason. And so those are just for additional practice if you want to. If I'm studying for the exam, what I'm probably looking at is going to be this practice exam A and this practice exam B. All right, so that's going to be some of the stuff that we're going to be going over today in class. If there's any specific questions, I'll kind of start with those. Otherwise, I'm probably going to pick and choose. Probably look a little bit more at the hypothesis testing problems and maybe walk us through that form of the sheet a little bit. Okay. Any questions for me other than that before we get started here? Yeah.
Just for clarification, you said the first section of the assignment was mostly to do with the norm.dist function.
Yep. So you're just calculating the first part, you're just calculating mean, standard deviation. And part B is where, excuse me. I'll even go over the hardest one, I think. So maybe I'm interested in the probability that I'm in between two values, right? I'm going to make up these values. They don't look anything like the assignment. But if I use that norm.dist function, all I need to do is tell it that cutoff value, the mean, the standard deviation, and then we always do comma 1 to make it cumulative. This calculates the z-score behind the scenes for us and returns to us the area to the left of that cutoff value. And then in this example, I would use that equation again, but now I've got a cutoff value of 20, right? Now the norm.dist function gives me the area to the left of 20, subtract that smaller area from the larger area, and I'm left with just what's in between. So just go all the way back to where you don't even have to calculate the z-score. I didn't ask you to do that. You can use that shortcut where use that norm.dist, you give it everything it needs, right? This was like X, gives you everything you need to calculate that z-score, right? It then looks at that z-score up in the table for you and gives you that area to the left, or that cumulative probability. Okay. Any other questions before we get started here? 1B on the Excel side. Yep. All right, so I'm going to go back and kind of do this just because it shouldn't take us too long. We'll start with practice exam A. Oh, let me try to get this out of here. So I have this example where I'm thinking about the amount of time that I wait at the DMV, right? I might actually change this a little bit from what we have in the exam, just to make it a little bit more difficult, right? For what we're going to do in class. So you've got this, you've got the answer key, so you can work through these values. I'm going to change the values a little bit just to show you something that might be a little bit more difficult, or something more like I might ask you on. So let's say, I've got a uniformly distributed variable, and let's say I do, instead of 0 to 62, 20 to 60. So anytime we've got this uniformly distributed variable, and I think on all these problems, it helps to draw out what we're doing. The uniformly distributed variable is the one where we just kind of have this flat line, right? Everything was equally as likely. So every value from 20 to 60, where we can kind of think about our maximum minus our minimum, is going to be equally as likely. So if I want the mean or the standard deviation of this uniformly distributed variable, if I've got the formula sheet in front of me, this should be pretty easy. So if I pull up that formula sheet, once again, I'm trying to be pretty nice. This formula sheet follows the order of how we've covered things in class. And if you'll notice, if you look through the practice exam, it generally follows the order of the practice exam. So you shouldn't be using like equation in the bottom right for the very first problem, right? So we're gonna be thinking about up here, we've got some equations that we're going to use for our uniformly distributed variable. If it's uniformly distributed, here's the equations that will give us our means and our variance. The mean was relatively intuitive, right? If everything's equally as likely, then the mean is just the value that's in between my minimum and my maximum. So how do I find the middle value? Well, I just add those two values up and divide by 2. That's exactly what we have there for our mean equation, right? Now, C and D kind of refer to our minimum and our maximum, so we might have to remember that. Once again, a good thing might be when you're studying for the exam, you have the formula sheet in front of you. Right next to this, minimum plus maximum, right? Where we see C and D, remember that, it's the minimum and the maximum, minimum, right? So, if I'm looking for the middle value here, just take that maximum, add the minimum, divide by 2, and that should give me that middle value. In fact, I'm probably going to be fairly nice and give you even numbers like this. I mean, like some of us might be able to look and say, oh yeah, the middle value is 40, right? Without even actually using the actual equation. So we've got this mean of 40. Okay? If I asked you for the variance, right, how would I find that? Well, I've got my equation here, my set of uniform equations. Sigma squared is our variance. So that should be as simple as take that maximum, subtract the minimum, right? We're looking at the range of possible values. And then we said we don't really have to go through why. There's a proof, mathematical proof that shows us the variance of a uniformly distributed variable will always follow this formula, right? I guess some questions like, where's the 12 come from? It just is, you know, if you work through the mathematical proof, it just is what it is. Okay. So we've got what? 40 squared divided by 12. I probably can't do this in my head, so I might as well have Excel pulled up here, so I can do this math for, actually, I already said it was 40. So about 133.33. Right? The only other thing I might ask you to do, and this is where we have to be careful, there's a few people who got this wrong on the first exam. What if I wanted, so this was, right, giving me my variance. What if I wanted the standard deviation? Just take the square root. Right, so make sure you're reading these carefully. If I ask you for the standard deviation of a uniformly distributed variable, we have the equation for the variance, but if we wanted the standard deviation, we'd have to take the square root there. Okay. We'll then do, I'll kind of do this, we'll go through 3 quick and then 4. So on 3, I'm saying, okay, what's the probability you're waiting in line? What's the probability you're waiting more than 35 minutes? Once again, I've changed the numbers from the example we have here. You go back through and work out, you know, these practice exam values. Might be helpful that I'm doing so through some different values here in class. So we've got this setup where the minimum's 20, maximum's 60, right? And I want to know what's the probability that was greater than 35. So I'm thinking about this cutoff value I'm interested in is 35. I'm looking for the area to the right, being greater than that. Well, right away, what do I know this probability has to be greater than? 0.5, yeah, 50%, right? Why? Well, because the area, same thing with a normal distribution and a uniformly distributed uniform distribution, they're symmetric. So the area to the left and the right of the mean will always be 0.5. So this is one of those things when you're thinking about these probabilities, is a good check just to make sure you don't make a simple mistake, right? Because you know right away this has to be greater than 0.5. Okay? On top of that, how am I actually going to find this, right? Well, we said with this uniformly distributed variable, I'm really just looking for the area of a rectangle here. Right? I know the base of that rectangle. I'm going from 35 to 60. So that's what? 25. Right? What's the height of that distribution going to be? Does anybody remember what that is? So we go to our formula sheet. Kind of has a reminder here that when I'm thinking about the height of my distribution, anything within the minimum and the maximum has a probability of occurring of 1 over the range, right? Or 1 over my maximum minus my minimum. So here I've got what, 1/60 minus 20, or 1/40. Well, now I've got the height of my rectangle, right? The height of my distribution. I've got the base or the length of my rectangle. So it'd be as simple as base times height. Or length times width, however we want to call this. I guess base times height usually for triangles, but right, length times width. Any questions on this? Okay. Now, if you really wanted to, you can use the equation that we have to kind of find the probability being between two values. Here, if I wanted to know if I'm greater than 35, I'm actually thinking I'm between 35 and 60. So that's kind of where my interval starts and stops. That's going to be my values for A and B. That's 60 minus 35. And then my maximum and my minimum, I'm going to have that. Or was it? Here it is. 60 minus 20. It's really the same thing we're doing here. I just think when you draw it out and think about it as finding the area of a rectangle, is something hopefully that we're already a little bit familiar with. And I think that makes it a little bit easier. Okay. So let's do one more. Any questions on that before I keep moving? Yeah.
That's the on the probability like a 35 or greater, right?
Yep. And then if I wanted to find the probability of being less than 35, it'd be the same kind of setup. But I'm looking for the area of this rectangle. Height's still the same, but the base is now 35 minus 20, right? Or the length, sorry, the length is going to be 30. I could even do something a little trickier, and this is where we could use some knowledge that we have to make it a little bit easier. So let's say I've got the same setup, minimum of 20, maximum of 60. And I say, okay, what's the probability that you're in between 25 and 30, or 45 and 50? Okay. Well, remember, we already had the height of this distribution. So what would I do? Well, I can find the area of this rectangle. That's just going to be what? The height is 1/40. The length would be, we're going from 25 to 30, so 5. Right? So 5/40. I don't know whatever decimal that works out to be, that's going to be kind of our probability. But I also need to find the probability I'm in between 45 and 50, but I actually don't have to do any work. I already should know what that is. What should that value be? 5/40, right? Uniformly distributed variables, every equally sized interval has the same likelihood of occurring. Both these intervals are of length 5. Right? So then I would have what? 5/40 plus 5/40, right? 10/40 or 0.25. Is that any questions on that idea? So if I ask you to do something like this, where I say, what's the probability of this or this area with a uniformly distributed variable? Wink, wink, I'm probably going to be giving you intervals that are the same length, so that if you know that equally sized length intervals have the same probability of occurring, it's not going to take you near as much time, right? You don't have to find the area of each rectangle. Once you find the area of one, you automatically know the area of the other. Okay? Any questions on that before we keep going here? So I think what I'll do next, unless there's any specific questions that anybody has, I guess I kind of jumped into this without giving a little bit of a pause here first. Is there any specific questions somebody has in these practice exams? Or what type of problems would you like to see worked through? No preference? All of them? So let's go here. I forgot to delete this one, so you can hit. This is probably going for me to mention. So let's start out with number 15. All right. So we've got what dentist salaries here, I think. And we've got a sample standard deviation. We've got a sample mean that we found 145,000 from 30 different dentists. So that's going to be our sample size. So we don't know what that true population mean or variance is. Right? I want to build a 90% confidence interval for dentist salaries here. What I'm going to do is, okay, look, I know that I'm trying to find a confidence interval. So I go to my formula sheet. and I've got three different types of confidence interval equations, right? We said we had three different setups, right? One, we had a sample mean where we knew the population standard deviation or variance. We're looking at proportions, both of those, and formula sheet kind of reminds me, I'm using the standard norm or the z-tables for those. For my sample mean, when I only have a sample variance, kind of reminds me, I need to be using that student t distribution. Okay, so I've got a samples, and I say sample variance, a sample standard deviation or a sample variance, right? If we know one, we can inherently find the other. Okay? So I know I'm going to be using this equation here, where I'm going to take my sample mean, and I'm going to add or subtract my margin of error, get my upper and lower bound. I want to find the number of standard deviations away I need to go to get alpha over 2 on each side of my confidence interval, or that t value. And then I multiply by the standard deviation of my sample means, which is simply the square root of the original variance that I sampled from, sample variance, divided by my sample size. Okay. So that's my equation. I've already got the information for most of this. So if I go back to that problem, right, I got a sample size of 30. Here I have to be a little bit careful because I have a sample standard deviation. So all I have is S. All right, and then my sample mean is 145,000. Let me start plugging these values in. So 145,000 plus or minus what 10,000 squared over 30. Now it might be helpful to kind of calculate this ahead of time, right? That standard deviation, just so I don't have as long of an equation to get entered into my calculator. So actually I'll zoom in so we can actually see this a little better too. So if I do that, I'm just gonna use Excel in my calculator here as we're kind of working, unless somebody else can get it before me. So about 1,825. So now the only thing left I need to do is find what that t value is. That's going to give me alpha over 2 on each side of my interval, right? So you'll kind of notice when we're doing confidence intervals, it's kind of like a two-tailed test, right? Which is very, very similar to a two-tailed test. So we're looking up kind of what t value would give me alpha over 2 in each tail. However, it's not a student t distribution, right? We have a different student t distribution at every single sample size or at every single degrees of freedom. So what would my degrees of freedom be here? How do I find that? Yeah, it's just n minus 1, right? So sample size minus 1, we got 29. So final step, of course, I did forget to do this at the beginning of the class. Get these Z and T tables pulled up, and I'll bring these for you on the exam. So you'll have Z tables, T tables, and formula sheets as well as the exam. So we go to our T tables. Maybe. I've got my degrees of freedom of 29, right? So I'm all the way down here. It's kind of a pain, but what's the area that I want in each tail? Well, I didn't write down yet. What level of confidence do I want? So I wanted the 90% confidence. So my alpha is going to be what? 0.1, right? It's just the decimal form, whatever is outside of my interval. So 90%, 10% is outside, 0.1. So 0.1 divided by 2, right? That's how much I want in each tail or on each side of my confidence interval. So 0.05. So this is the area that I want in my tail. And then go down this column to that degrees of freedom of 29. 1.699 is going to be the number of standard deviations away I need to go to the left, right? Or subtract that to get my lower bound. Number of standard deviations I need to go to the right, or add that to get my upper bound. Okay. Any questions? Yeah. Yep. So so when it comes to hypothesis testing or confidence intervals, if I know my population variance and I'm looking at a sample mean, or I'm dealing with a sample proportion, I get to use those standard normal tables, right? The whole problem was when we only have a sample variance, we're dividing by n-1 to calculate that. So we know even if it was 100% accurate, it's gonna be a little bit off. It's gonna be a little bit overinflated. So whenever we only had a sample variance or a sample standard deviation, we had to use that student t distribution. So. Yeah, and this applies to both confidence intervals and hypothesis testing. And you know, I actually will probably be even kinder in the exam. So if this was an exam question, this is likely what it would look like. I'd be a little bit more intentional about making sure I bold or capitalize, somehow making sure you see, look, you've only got a sample standard deviation there. It's not this known population standard deviation or variance. Any other questions before we kind of keep moving here? Hopefully for the final, I'm not necessarily working through all these. I'm sure the answer key's there. So, you know, hopefully once we plug everything in, you can try to make sure, you know, you can get this entered into your calculator correctly. Like I said, sometimes where I see some of the issue being maybe calculating this ahead of time, just kind of breaking it down to steps, sometimes helps a little bit. And if you do that and you're rounding it to the second decimal or something, you may be a little bit off of what the answer is, like depending on where you round it to. I'm never going to be giving you two answers where the rounding is going to make you, you know, it should be really, really close, right? You're never going to be like equally between two answers. Now, if you enter it in, you're out there like this, you'll get exactly kind of the numbers I'm showing up there. Excuse me, but as long as you keep this out to the third or fourth decimal, you should be fine. Okay. Any other questions on that before we keep moving? Okay. So to enter here, so we get this, maybe so it's all on one. There we go. So let's scroll down here. We'll go to keep using the same values here. And actually, did I accidentally create a different question? So this should be 16. Oh, here. There we go. So we go down to 16. We've got, okay, there's something that publishes this information. What is it? The US News publishes that the average dentist salary is 150,000. You're not convinced, and you think that it's less than that amount. Right? So I want to test for whether or not the dentist salary is less than this reported amount of 150,000. Okay? So whatever I want to test for, that's my alternative hypothesis. So if I'm trying to just identify the null and the alternative, it's always best to start out with that alternative. We usually phrase things in what we're trying to find, what we're trying to test for. So what I'm trying to test for here is that true mean for dentist salaries less than 150,000? The null hypothesis is going to be the exact opposite of that, which is that it's greater than or equal to 150,000. Now, if I'm looking at these right away, what term, I mean, you may not remember if you watch the video real careful, but what term is going to kind of let us know we got a not equal to sign or a two-tailed test? The term there that you're looking for to identify if you got a not equal to sign or a two-tailed test is going to be, is it different than a certain amount, right? Or is it different from a certain value? Because being different, you can see evidence on the left or the right, and it will go against it. Here, we're very specific that we just want to know, is it less than 150,000? So I look at my alternative hypothesis, and we can kind of think about, I've got a less than or a left-tailed test, where only evidence on the left is going to go against the null, right? So if I see, you know, a sample mean of 170,000, it's pretty easy. I don't even have to go through the hypothesis test. I already know that I'm going to fail to reject the null. I found evidence that supports it. So only evidence that's on the left side of my distribution or below 150,000 is going to be things that are interesting, right? Evidence that goes against my null hypothesis. So I'll try to leave this up here just so. So the next question, and this is one, I think I forgot to delete one, so I'll tell you which one you can kind of ignore here in a second. Yeah. So you can ignore 17. I apologize, probably was going to start class, so I apologize that my life stuff kind of took me out of class, and this is, you know, I know that kind of had to go through hypothesis testing a little bit different. So I usually go through another topic before we get to this exam. I kind of punted on that. We're gonna save it till afterwards, so we don't have to worry about critical values. All right, so don't worry about this question about critical values. I already had the practice exams made up. I meant to go back and then delete that. I'm not gonna expect you to know how to do critical value stuff. We just talked about p values, okay? So ignore this one. And then we get down to 18. We want to know, how do I calculate my test statistic? Okay. Well, if I go to that formula sheet, down here, I've got 3 different test statistic equations. 2 of them are Z statistics, right? Coming from that standard normal distribution. One of them is a T statistic, test statistic coming from the student T distributions. It's going to follow the same thing as confidence intervals. If I know the population variance, I'm dealing with a sample mean, or I've got a sample proportion, so that's these 2 situations here. This is how I'm going to turn those sample statistics into z-scores. If I've got a sample mean where I only have a sample variance, this is the equation I'm going to use to turn that into a t-score, right? Or the number of standard deviations away from them, or the assumed true mean, sorry. So they still represent the same thing. They're the number of standard deviations, not away from the true mean, but away from the assumed true mean. So you'll notice, like this equation here and this equation down here looks the same as these 2 equations up here, with the exception of this was when we were dealing with, we knew the population proportion or we knew the population mean. Excuse me, we now just have an assumed true mean and an assumed true proportion. So it's not like we technically don't have Z and T values, we have Z and T statistics. It's just semantics kind of saying, you know, terminology letting us know it's the distance away from the assumed true mean. So my assumed true mean is that value I'm using in my alternative and my null hypothesis. So if I'm looking at this equation, right, my sample mean is, and we go back to the question, I believe it was 140,000. Of course, I erased everything now, so I have to do this from memory. We subtract that assumed true mean, which comes from our null and alternative hypothesis. We then divide by the square root. This is where we have to be careful again, because we were given the standard deviation. Well, what's in that denominator there? That's the variance. Now you'll notice there's another form of this equation written a little bit differently mathematically, but if I only have the standard deviation, this might be a little bit easier to use. But you could use either one. The difference is if I've only got the standard deviation and I use that first form, I need to make sure that I still remember I've got a square, right? Because that's just the standard deviation. I need to be plugging the variance in there. Okay? And then I divide by the sample size, which I think was 30. Okay? So this should give me my test statistic. These test statistic equations, it's really going to be a matter of making sure you can use your calculator correctly. You've got the formulas in front of you. I'm always going to give you the information. In fact, what I will do on the exam that I didn't do here in this practice exam, and it's because you have the answer key. But right, if I got the null and alternative wrong, and I chose the wrong, you know, I said I chose 145,000 or something else here, I can't get the test statistic right. So often what I'll do, I'll ask you for that null and alternative hypothesis. Then in the next question, if I ask you to calculate the test statistic, I say, assume that this was the null and alternative hypothesis, right? So you'll all be starting out, you know, with the same assumed true value, just in case you messed up earlier. Okay. But like I said, you've got the answer to here, so you can go through, you know what the true null and alternative should be. Any questions on this before you keep going? Yeah. Yeah, so I was just running off the same example, so I'll do this on the exam too. It's a good question. I'll give you this information, like we took a sample, find the confidence interval, then go writing the hypothesis testing, but not giving you a whole new set of values, right? So hopefully it makes it a little bit easier where you keep using the same sample size, sample mean, and usually I'll do something like this where I indicate, use this information for the next X number of questions. Any other questions before we keep moving here? Also, sorry, I feel like I get excited sometimes when I feel like I'm shouting at you guys a little bit this morning. So we've got this test statistic. We'll go down. The next thing that we're going to look at is very similar to what I'll do on the exam. You could have gotten the test statistic wrong, right? So what am I going to do? I'm going to give you an assumed true test statistic, right? Doesn't matter what you found in the previous problem, assume this was the test statistic that we found. And I can't reiterate this enough. I'm choosing these values not because they're close to what the correct answer is. So in fact, sometimes I choose them to be the opposite of what the correct answer is. So do not read into these values at all for what the correct test statistic should be. I think in this example, they're both negative, so it might make a little bit of sense, but on the exam, the test statistic you find might be negative, I might give you a positive test statistic, right? It just depends on the principles I'm trying to test and what I want to do. So, but I want to make sure we're all starting off on the same foot. So we've got this known test statistic of negative 1.5. Now this one's kind of easy, right? Because what type of tail test do I have here? I've got a left tail test. So if I'm looking for a p-value, which I believe is this, what we're going to need in order to answer the question, in order to say whether or not I reject or fail to reject at different levels of significance, I need to know, is that p-value less than alpha, right? What are the alphas that we typically compare to? Same as our confidence intervals, 0.1, 0.05, and 0.01, right? Or those kind of correspond to 10, 5, and 1% significance levels, or the 90, 95, 99 confidence levels. Okay. So I'm trying to find the p-value. What is the p-value? Well, the p-value is the probability that I saw something as far away from the assumed true mean that I found, or something even further. Okay. So if I'm trying to be a little bit more complete here, if this was the true test statistic, right? Our sample means should have been centered around whatever that assumed true mean was, 150,000. We found a sample mean of 145,000, and we turned it into a test statistic, right? Or this t-value. Okay? So my p-value, the probability I saw something as inconsistent with my null hypothesis, or something even more inconsistent for a left-tailed test, is the area to the left. If we're dealing with a right-tailed test, something even more consistent would be the area to the right. And I'll kind of talk about two-tailed tests after we work through this example. So I'm just looking for the area to the left of this test statistic. How can I find that? I go to my student t-table, I go to my degrees of freedom of 29, which we talked about already for the confidence intervals, right? Same kind of idea, sample by the, and I look up this test statistic. Now, on the exam, I'll be a little bit kinder. So if we looked here, and I went to my degrees of freedom of 29, well, first of all, I don't have negative values, but we said it doesn't matter. It's a symmetric distribution. So the area to the left of negative 1.5 will be the same as the area to the right of positive 1.5. Okay. Well, I don't have 1.5 here. I'm in between these two values. So what I could say is, well, look, I know the area to the right of those two values is 0.1 and 0.05. So my p-value is somewhere in that range. Right? On the exam, I won't be that mean. I'll give you an assumed true test statistic that would be something like, negative 2.045. I'll give you a value that's in that table. I'm not going to make you kind of put the p-value in range. You'll be able to find the exact test statistic that I'm giving you. You then go up, okay, at my degrees of freedom of 29, my test statistic is 2.045. The area in the tail that would give me is 0.025. Okay. Any questions on that? Like I said, when I wrote this exam or practice exam, I might have thought about putting these into ranges, which is why I use them. Well, on the exam, I'm not going to make you put that p-value in range. I'll give you one of those specific numbers that's in this table. So I've got this p-value of 0.025. Right? Changing this a little bit from kind of the practice exam. Once again, seeing a different value, maybe a little more helpful. If my p-value is 0.025, which levels can I reject that? I mean, this one, if you're just looking at the numbers, maybe you make a mistake. I'm hoping you write this out is 0.025 less than 0.1. Yeah. So this is my rejection decision. This holds. I reject. So I can reject at the 10% significance level. Is 0.025 less than 0.05? Once again, if I write this out, hopefully it's kind of easy to see. Yes. So I reject at that level. Is 0.025 less than 0.01? No. So I fail to reject at that 1% significance level. So if I'm going back here, And I think this is a little bit different than what the answer key says because I changed their test statistic on us. But if we were actually answering it with that test statistic of negative 2.045, we reject at the 10 and 5% level only, right? We fail to reject the 1%. And just to point out, which of these makes no sense at all. If I can reject at the 5 and 1% level, I mean, that would mean my p-value is less than 0.01 and 0.05. How the hell could it not be less than 0.1, right? So we can always reject at higher levels of confidence or higher levels of, lower levels of confidence, higher levels of significance, right? I can reject at the 10% level sometimes, but not the 5 and the 1. There's never going to be a situation where I reject at the 1% level, but not at the 10, right? That'd be like saying I can reject it with 99% confidence, but I can't reject it with 90, right? That doesn't make any sense. So we could rule out, what was it, C? Yeah, C right away. Okay. Questions on that before we keep going here? Okay. And you know, a lot of these different, so if I went through a different scenario, so I don't have time to work through every single example. If I had an example where I had a known population variance or a sample proportion, when I'm finding the p-value, it's really going to be the exact same steps. It's just that I've got a slightly different equation to calculate that test statistic. But once I have that test statistic, instead of looking up the t-table, I would look it up in the z-table, find the area in the tail. That's my p-value. Compare the p-value to alpha to make my rejection decision. Okay, so it's still following the same steps. It's just I'm using a different distribution here, and we'll be able to work through one of these here in a second. Before I do that, let me double check to see which one of these is a two-tailed test, and I'll see how we proceed. So let's see. Do I have? Okay, let's do this one. So let's go back up to. Now I think I accidentally added another question again. Question 11, right? I'm just going to try to get this so it's all in one. But before I continue, any questions on this one before we keep? Okay. So question 11, I'm looking at what? For a portion of athletic programs in NCAA, they have a positive problem, right? So I want to know whether or not it's different than 45%. So before I even get going, I've got a sample proportion. Anytime I see the word proportion, throw the t-table to the side, right? We always know we're looking at that standard normal distribution. Okay? What am I trying to find, or what am I trying to test for? Well, that's going to be my alternative hypothesis. I want to know, is that proportion different than 0.45? Like I see this term different than, what should be in that alternative hypothesis? Two-tailed test or a not equal to sign. Yeah. So I want to know, is it different than or not equal to that proportion of 0.45? So sometimes we might phrase it in a percentage. We always know we can convert a percentage to a proportion by just moving that decimal two places. So that would mean my null is the exact opposite of that, which is that it's equal to 0.45. So I know I've got a two-tailed test. The first step I'm going to ask you is find that test statistic. Okay. So I've got my test statistic, got my test statistic equation on the formula sheet. So I'm going to look that up. I know I'm dealing with a standard normal distribution. I go here, I've got proportions. I'm going to be dealing with this guy right here. So I take my sample proportion. Well, I didn't write that down, so go back. Okay, where did I go? Oh, it's all the way up here. Sorry. So here's I did a confidence interval one. I'm going to skip the confidence interval so we do a little more with hypothesis testing. The original kind of information I was given is I took 40 schools and I found that 55% of them had a positive profit amount, right? So I've got a sample proportion of 0.55 and a sample size of 40. Okay. So when I go to that formula sheet, I'll take that sample proportion that I found, 0.55, subtract the assumed true proportion, which comes from my null alternative hypothesis. That's my p subscript 0. Divide by the square root of that population, or sorry, assumed true population proportion times 1 minus that assumed true population proportion, and then divide by that sample size. Okay. once again, these test statistic equations, I mean, hopefully you can kind of see. I'm using the notation in the question. Hopefully then when you go to the formula sheet, you're looking for a test statistic. Here's your 3 test statistics. Which one has p hat in it? All right, which one's dealing with proportions? This guy does. Another thing, kind of, once again, that can sometimes help. This represents our standard deviation of that sample statistic. Sometimes calculating this ahead of time so that you just have one value to plug into the denominator there. It kind of helps some calculator error. Okay. Any questions on this before we keep moving? Okay with that for right now? Right. So I think the next question is the one that we can ignore, which is asking about critical values. But, and I don't know what this is off the top of my head, so let's look at these and I maybe hopefully can guess. So I think if I plug this into my calculator, my guess is I get 1.27. Does anybody want to check me there? Or I can kind of use Excel real quick. So what, 0.1 divided by the square root of 0.45 times 0.55 divided by 40. Yeah, so about 1.27, right? Is going to be my value there. So that's my Z statistic or my test statistic that I found. Okay. Just plugging this into my calculator. Now I have a two-tailed test, so my p-value is the probability I saw sample evidence that was as inconsistent with the null as what I found, or anything even more inconsistent. But now remember, these z values, or this z statistic, came from the fact that I had this assumed true proportion of 0.45. I found a sample proportion of 0.55. So I found evidence that was on the right side of the distribution. So the probability that I saw something as inconsistent with what I assumed to be true as what I saw. I'm sorry, someone should have called me out. It wasn't 1.47, was it? It was 1.27. I wrote the wrong number. So probably I saw something as inconsistent with the null as what I found, or anything even more inconsistent. What we kind of think about is this area in the right tail. The problem is with a two-tailed test, I only took one sample. But it would have been equally as likely for me to see something that was that far away from that assumed true mean, but on the other side of the distribution. So every single value here, I have a value that was equally as likely for me to see and would have been equally as damning to that assumed true value, right? Because now evidence on either side of my distribution goes against my null. Before, it was only one side. Right? I was assuming it was greater than or equal to. So nothing on the the right side would have been against null. Here, I'm assuming it's exactly equal to a certain value. If I see stuff on the left or the right, it would go against that. So now when I look up this area, I'm going to have to remember that for a two-tailed test, to find my p-value, I need to multiply that area by 2. Okay. So how do I find that area? Well, I've got my z value. So I go to that z table. I'm going to look up 1.27. So 1.2, I'm on the right line here, 7, so 0.8980. I multiply this by 2, I get what, like almost 1.8? Why do I know I made a mistake if I get 1.8 from my p-value? The definition of my p-value is the probability I saw something as far away from the null as I found, or something even further away. What's the highest that could ever be? 1. That's a probability. So remember, this p-value is still a probability. So what did I do wrong here? When I looked at z value of 1.27 up in the table, it's not the area to the right. That 0.898 is actually, or 8980, is actually the area to the left, right? The table kind of gives me that area to the left. I wanted the area to the right. So I should have been subtracting that from 1. Right? So here, I don't know, what's this 0.102 times 2, so 0.0204, if I'm doing the math in my head correct there. Or not 0.2, sorry. 0.204, right? Not 0.02. Any questions on that? So it's a little bit tricky with a two-tailed test if we have a positive test statistic. Because when I looked at stuff in my table, the table's giving me the areas of the left. I want the area in this tail or the areas of the right, so I need to subtract it from 1. Once I have the area in this tail, which is what, 0.102. For a two-tailed test, that's only half of my p-value. So I then need to multiply that by 2 to get my total p-value. Okay. Any questions on that before I keep moving here? If this is a right-tailed test, what would be the only thing that's different? If it was a right-tailed test, I want the probability I saw sample evidence as inconsistent as what I found or anything even more consistent. But now, values on the other side wouldn't go against the null. So the only difference if this was a right-tailed test, I would still find the p-value the same way. I just wouldn't multiply it by 2, right? The only time you multiply that area by 2 is if you're dealing with a two-tailed test or you have a not equal to sign in that alternative hypothesis. Is that clear? Any questions on that? Keep going here. Just want to do, we have enough time, just 2 more things. So we didn't quite complete this. I'm guessing the next question was something like, what levels can we reject this at? Or maybe I asked you for the p-value and what levels you can if you can reject it at a certain level. So get rid of this. Our p-value is now 0.204. So which levels can I reject the null hypothesis at? At least my benchmark ones. Is 0.204 less than 0.1? No. So if it's not less, I fail to reject. If it's less than, I reject. So if it's not less, then I fail to reject. Well, if it's not less than 0.1, sure as hell isn't going to be less than 0.05 or 0.01. Okay. So, any questions on that one? Shouldn't be too bad. So if you have like a really high p-value, the rejection decision part becomes kind of easy, right? It's not going to be less than any of these, right? So I would say I fail to reject at every level, or I can't reject at any level. Right? There's no level I can reject at least of my benchmark rejection levels. I want to go through one thing. Let me write something out for us here so that we can see this. If I write that test statistic equation down without plugging our values in, it looks something like this, right? So what happens if I then, I think this is, I asked this on a further question, so I'll kind of try to give you one that this relates to. I think this is down here at 20, right? So let's say, it could apply to anything. It could apply to a proportion example. It could apply to the example where I had a sample mean with a sample variance. But let's say I take a higher sample size, okay? So if I take a higher sample size, which of the following is going to be true? So I've got statements about what? The test statistic, the p-value, and whether or not I'm more or less likely to reject them. So if you write the equation out, it can often help you with this. But once we work through it, I'll just give you a nice synopsis, maybe write it down, remember this going into the exam. If I've got a higher sample size, what's going to happen to my test statistic? Well, if this denominator is larger, what happens to this fraction? Smaller. If this denominator is smaller, what happens to this fraction? Divided by a smaller number, it's going to be higher, right? Seeing sample evidence the same distance away from the assumed true value at a higher sample size is going to be a higher number of standard deviations away. Because taking that higher sample size reduces the standard deviation. Remember that this denominator represented the standard deviation of that statistic. Okay? So I'm going to end up with a higher test statistic. If my test statistic is greater, what's going to happen to my p-value? Well, the area to the right is going to be smaller, right? So I'm going to end up with a smaller p-value. And if I have a smaller p-value, am I going to be more or less likely to reject the null? If this p-value is smaller, well, it's going to be more likely it's less than the alpha that I set, right? The closer that p-value gets to 0, the more likely it is I can reject the null. Right? So once again, if you write the equation out and kind of think about just the mathematics of how the test statistic changed, plotting that test statistic, how does the p-value change? But the end result of the story is higher sample sizes. It means it's more likely that we can reject the null. All right, so kind of know that going in, and the opposite is true as well. Smaller sample sizes, less likely you can reject the null. So I'll post this up. I might work through some slightly different problems with my next section. I'm going to be putting 2 videos up today. If you want to kind of look through that, you just have an additional resource. Other than that, office hours 3 to 5 today and tomorrow. If you have any questions about the homework of the exam, please feel free to reach out. Other than that, I'll see you guys on Wednesday. Or sorry, Friday. Today's Wednesday.